welcome Mark.
Hi everyone, my name is Mark Yamani. I'm a junior at Eckerd College in St. Petersburg, Florida, and I studied computer science and marine science, and I'm presenting to you from Shoreline, Washington, which is the first city north of Seattle. This summer I had the pleasure of working with Mariona Claret and Pascal Lalonde on near-inertial wave interactions with cyclonic and anticyclonic eddies in the northwestern Mediterranean. So for background, we can think of near-inertial waves as surface waves, the ones we see when we look out at the ocean, but these ones can propagate downward due to density differences within the ocean. And they propagate downwards when they're in an eddy field. Eddies are circular currents, like what Victoria was talking about. They're circular currents. They can be as small as the little currents you make when you stir a cup of coffee, for example. But the ones I was looking at were sub-mesoscale and mesoscale eddies. So these range from 1 to 30 kilometers in radius, so a little bit bigger than the ones you find in our coffee. And so something interesting to know about eddy rotation is that the direction actually impacts how they interact with waves. So cyclonic eddies are known to repel near-inertial waves, while anticyclonic eddies, which are clockwise, flush near-inertial wave energy downwards. They provide a lot of energy to the ocean interior, so this is why we're interested in this interaction. This is also called an inertial chimney mechanism. And so the Mediterranean Sea is a natural laboratory for studying ocean dynamics. And so the questions I was looking at in this area are, is this inertial chimney mechanism present, and how are waves interacting with eddies in this area? And this animation is showing you this near-inertial wave getting trapped with this anticyclonic eddy. So this map in the background is the Mediterranean. You can see streamlines of the major currents of the Mediterranean. And there's a box around the Gulf of Lion, which is the area I studied. So you can see these major currents, but I used a high-resolution ocean circulation model. High resolution so that we can see these finer scale motions within these major currents. So you can see these, this is eddy centers and shapes at 500 meters from an eddy tracking algorithm. It's plotted over the Gulf of Lion, contoured by Rossby number. Rossby number tells us eddy intensity, where blue, the negative numbers, negative Rossby numbers are clockwise rotation. These are anticyclonic eddies. And red is showing us counterclockwise rotation, or cyclonic eddies in this area. I looked at eddy statistics to learn more about the eddies themselves in this area, and then rotary spectra to learn more about the eddy-wave interaction. So here are some histograms I created. To interpret these, the x-axis is on the left, right here, lifetime in days, and the y-axis for here is percent of the eddies at that depth. And so what we're seeing here is that a longer lifetime led to a greater propagation. This distribution is becoming more full at depth. And this makes sense because with the longer lifetime, these eddies have more time to propagate. And at the surface, we're seeing a lot shorter lifetime. This also makes sense because the surface is very dynamic. So while the lifetime is very short, we're seeing more than 3 times as many eddies in the area. I also looked at Rossby number and radius. Rossby number, again, is eddy intensity. So we're seeing this decrease by an order of magnitude at depth, meaning that these eddies are getting less intense with depth. And something we know about radius, eddy radius, is that a smaller radius correlates with a smaller Rossby number. And so that you can see that here, although it's less apparent. I also looked at rotary spectra. So I used Fourier transform to decompose this a time series of the horizontal velocities into its frequency components. So you can interpret the x-axis as negative values being, again, the clockwise rotation, and positive values as counterclockwise rotation. At 0 is mean flow. So this peak here is showing us the average of all the major currents. We can think of this as background. And I normalized the x-axis by Coriolis frequency. So every 1 in this frequency is around a 17-hour period. And I did this normalization so that we can interpret the -1 peak to be near-inertial waves. So we see this near-inertial waves at the surface, but we also see it propagating to depth. We see it at the 500 meters and 1500 meters rotary spectra of the open ocean. I also made rotary spectra following the eddy center. So using the eddy tracking algorithm, I computed the Fourier transform at each of these centers. And we see this peak at the surface again at -1. We see it at 500 meters, and here we can start seeing the eddy interaction where the anticyclonic eddies are making this sub-inertial. And so this means that these ones are actually being trapped within this eddy. The cyclonic are super inertial, meaning these ones are getting repelled. And these modifications are less apparent, are less intense at 1500 meters, and this correlates with the smaller Rossby numbers at depth. So we saw that there are more cyclonic eddies and anticyclonic eddies at the surface. We saw that these near inertial waves were present in the rotary spectrum of both the open ocean and the following eddy centers. The ones following eddy centers showed to suggest that these inertial tuning mechanisms were present. And future studies could include analyzing eddies over a longer time scale at different depths. And then there's also this spectral peak at positive one, which is something to look into. It was out of the scope of my project for some reason. So special thanks to Mariana and Pascal for teaching me all of this. I learned so much over the summer. Thank you to Jed for organizing the internship program, Giannis for the eddy trapping GIF, and the Seacoast and NWRA community, and my fellow Seacoast interns for making this such a meaningful summer internship. I learned a lot. I did a lot of coding also. I saw this as my opportunity to make my own QR code. I've always wanted to put one on a poster. So if you want to check out all the code I made for analysis and making the figures, you can go to my GitHub or scan this QR code. Thank you for watching.
Yeah, thanks, Mark. Definitely go to that QR code. That was a good idea. Any questions for Mark? Everyone's going to the QR code right now, so they don't have questions.
That makes sense. That makes sense.
You answered everything. Okay.
As they should be.
We do have one from Haley, though. What do you mean when you said that the Mediterranean is a natural laboratory?
So we can think of it as like a smaller representation of the global ocean because they share a lot of the similar features. So within the Mediterranean, it's incredibly dynamic, and so we can see things like deep water mass formation, thermohaline circulation, and then more specifically for my project, we could see the near inertial waves and the eddy fields. So we can use the Mediterranean as like a microcosm of global ocean.
Cool. Yeah, and one last question. Is there a reason that there were more cyclonic than anticyclonic eddies at the surface?
Globally, that's a good question. Globally, eddies, this ratio between the two varies between regions. So that I think this just happens to be what it's the ratio for this region. It varies everywhere, so it's kind of it differs between areas.
Okay, great. Thank you, Mark. So that's it. That was our final presentation of the day. So thank you all for coming. We're now going to transition into the poster session portion. So all of the students who just presented are going to be leaving this meeting